The paper emphasizes the significance of high-order interactions in various systems, including social, ecological, and biological systems, which cannot be fully understood through pairwise relationships alone. It underscores the necessity for a systematic approach to detect and measure these interactions from data. The authors introduce a hierarchy of order interaction measures that are increasingly inclusive of possible factorisations of the joint probability distribution. They also define non-parametric, kernel-based tests to establish the statistical significance of order interactions. This work draws connections with lattice theory, elucidating the derivation of the interaction measures and their composite permutation tests, and clarifies the connection of simplicial complexes with kernel matrix centering. This research aims to provide a comprehensive framework for identifying and quantifying high-order interactions in complex systems, with implications for understanding and modeling real-world phenomena. The research paper discusses the detection of high-order interactions between variables in observational data, extending kernel-based hypothesis tests beyond pairwise and three-way interactions. It introduces a family of tests that systematically generalize to any order D, with the Streitberg interaction test capturing all factorizations of the joint probability distribution. The authors also utilize lattice theory to provide a coherent theoretical foundation for detecting high-order interactions. They detail the conclusions that can be drawn from rejecting the Dorder-Lancaster interaction. The paper includes numerical validations of these tests on synthetic data and applies them to real-world neuroimaging data. The authors delve into the limitations of joint independence in identifying high-order interactions among multiple variables. They introduce the Lancaster interaction, a signed measure that can detect non-factorizable joint distributions for three variables. This measure is defined as increment cubed _ LP equals PCOVALENTP1P23D phosphorus trideca phosphide triphosphorus dodeca phosphide plus 2PD phosphorus triphosphide, which vanishes if the joint distribution can be factorized in any way. However, this measure fails to identify high-order interactions for four or more variables. To address this limitation, the authors propose the Streitberg interaction, a more general interaction measure defined using partitions. The Streitberg interaction is defined as increment to the power of 4 _ SP equals _ pi element of pi, d, pi, 1. 1, pi, 1, p pi, where pi, d, is the set of all partitions of the random variables, and p pi is the corresponding factorization. This measure has been proven to vanish if the joint distribution can be factorized in any way. The authors also introduce the concept of partition lattices, which can be used to systematically generate the interaction measures. A partition lattice is a partially ordered set defined on a set of random variables, where the ordering is given by the notion of partition refinement. The authors show that the interaction measures can be obtained by defining a sum function on the partition lattice, which is analogous to the integration of a real-valued function over the interval 0, pi. The partition lattice structure allows for the definition of the least upper bound and greatest lower bound between any two partitions, and the interaction measures are obtained when the sum function is the probability distribution function. This formalism provides a systematic way to generate interaction measures and establish theoretical links with simplicial complexes. The Streitberg interaction, defined through the Mobius inversion over the complete partition lattice, is contrasted with the Lancaster interaction, obtained by defining the inversion over the Lancaster sublattice, consisting of partitions with at most one non-singleton block. The Lancaster interaction considers fewer interactions, resulting in fewer terms in its Mobius inversion. For dimensions d is greater than or equal to 4, the Streitberg and Lancaster lattices, and consequently the interaction measures, differ due to the presence of extra partitions with two non-singleton blocks. A connection is established between partition lattices and simplicial complexes, a popular representation of high-order systems. The subset lattice of A, D1, simplex is isomorphic to the Lancaster lattice, and the boundary matrices of A, D1, simplex appear as block matrices in the zeta matrix and the inverse Mobius matrix of the Dorder partition lattice. However, the full partition lattice provides more information compared to measures originating from sublattices, including the Lancaster lattice and its related simplicial complex construction. The interaction measures can be utilized as statistics in non-parametric tests when embedded into reproducing kernel Hilbert spaces, RKHS. Given a symmetric, positive definite kernel function, an associative RKHS can be constructed, and the kernel mean embedding of a probability measure can be defined. The kernel mean embedding satisfies the reproducing kernel property, enabling the creation of meaningful non-parametric tests by computing the kernel mean embedding of desired interaction measures. The Lancaster interaction is extended to the devariate case, and a family of interaction tests is formulated, including the Streitberg interaction, the Lancaster interaction, joint independence, and a generalized interaction. Proposition 1 establishes the necessary conditions for the Lancaster interaction to vanish, which is satisfied when the joint distribution can be factorized into partitions with at least one singleton. The mixed central moment operator is defined as the kernel embedding of the Lancaster interaction, expanding on equation 2, from reference 27. It's denoted as MD and expressed as a sum of moments, as shown in equation 5. This operator can be simplified to a central moment, eliminating all partitions except 1. As stated in proposition 2, equation 6. The entries of the matrix key are defined as key, she, for IID samples she, and the centering matrix H is used to obtain key. The norm of the embedding serves as a test statistic, with the estimator derived as a v-statistic, given in proposition 3, equation 7. The mixed cumulant operator is defined in terms of kernel embeddings from the Streitberg interaction, as shown in definition 2, equation 8. This operator can be simplified similarly, as stated in proposition 4, equation 9. The partitions with singletons are eliminated after centering, and the remaining partitions without singletons form an upper semilattice. The relationship between the mixed cumulant operator and the mixed central moment operator is established in lemma 1, equation 10. Where the mixed cumulant operator is equal to the sum of mixed central moment operator products associated with partitions with no singletons. When D equals 2 or 3, K'd and MD are identical, confirming the moment cumulant relationship. The partition lattice is discussed, with 0, 1, subset equal pi L subset equal pi, where pi L is the set of partitions in the Lancaster lattice, and pi is the full set in the Streitberg interaction. The estimation using a v-statistic for the norm of the Streitberg interaction is also provided. The Streitberg interaction estimator computes the norm of interaction operators through Mobius inversion of the Cartesian product of the upper semilattice, eliminating the need to square the operator. This approach enables direct calculation of test statistics from the product lattice, as detailed in the appendix. The interaction test involves rejecting the null hypothesis that the joint distribution can be factorized, encompassing the Lancaster interaction test, which rejects factorization into partitions with at least one singleton. The number of subhypotheses to be tested corresponds to factorizations with only 2 blocks, forming the second level from the top in the partition lattice. To efficiently test each subhypothesis, observations are fixed in the largest block, and permutations are applied to the remaining variables. The Monte Carlo approximation is used to compute the p-value, with a simple correction applied for multiple hypothesis testing. The permutation test algorithm involves computing the test statistic, initializing an empty vector, and iterating through observations to compute the p-value. The test rejects the null hypothesis if all corresponding subhypotheses are rejected. The authors discuss the application of Streitberg and Lancaster interactions to test for joint independence and marginal independence, highlighting their value in testing lower-order independence hypotheses where factorizations can lead to vanishing interaction measures. They introduce a generalized interaction measure that can handle interactions within multiple groups of variables, achieved by formulating an interaction measure based on a partition lattice. The generalized interaction operator increment pi SSP is defined as a sum of Mobius coefficients over all blocks in the partition pi S, with the condition that blocks have at least 2 elements. The authors explain that the generalized Streitberg interaction measure can be expressed in terms of ordinary Streitberg interaction measures. Computational considerations are also discussed, with the Lancaster interaction estimator having a time complexity of O(dn squared), and the Streitberg interaction estimator reduced to O(n min) pi s plus 1. The possibility of further reducing time complexity in a recursive setting is also explored. The validation of high-order interaction tests on synthetic datasets and their application to neuroimaging data is discussed. The comparison of the DHSIC test with the Lancaster and Streitberg interaction tests on multivariate Gaussian distributions and a 5-way XOR example shows that the DHSIC test fails to detect partial factorisations in both cases. In contrast, the Lancaster and Streitberg tests successfully capture these factorisations. The Streitberg test demonstrates higher power in detecting joint independence with fewer samples in the XOR example. The tests are validated using Gaussian kernels and the median heuristic for bandwidth. The authors investigate the concentration of high-order interactions in brain resting state networks using the Streitberg interaction test. Figure 3 presents the results, showing that 2, 3, 4, and 5-way interactions are significantly more common among regions belonging to the same resting state network, RSN, compared to random sets of regions. This supports the hypothesis that high-order interactions are more probable within RSNs, which are known to perform similar functions. The authors also compare the performance of the Streitberg interaction test with the Lancaster test and a modified DHSIC test in detecting high-order interactions. They find that the Streitberg test outperforms the modified DHSIC test, requiring a smaller sample size to achieve comparable performance. Additionally, the performance of DHSIC degrades faster than that of Lancaster and Streitberg as the sample size decreases. In the neuroimaging dataset, the authors apply the Streitberg interaction test to detect high-order interactions in brain activity data from 50 unrelated subjects. The dataset consists of resting state fMRI data, where each subject has 100 time series capturing the activity of each region in the Schaeffer Brain Atlas. The regions can be divided into 7 groups called resting state networks, RSN. The authors take temporal averages to obtain the mean activity per region and subject, and then perform the Streitberg interaction test on sets of brain regions either taken from within the same RSN or sampled at random from the whole brain. The results show that high-order interactions are more common among regions within the same RSN, confirming that the interaction test can successfully detect high-order interactions in real-world data. Notably, the authors find a larger percentage of two-way interactions in the somatomotor, SOM, and visual, VIS, networks compared to regions such as the frontoparietal network, FPN, or dorsal attention network, DAN, suggesting increased redundancy in these regions. In this work, the authors establish formal connections between lattice theory and a family of high-order interaction measures based on factorisations of the joint probability distribution. This connection facilitates the derivation and interpretation of these measures, highlighting their relationship to simplicial complexes and other sublattices. It also aids in formulating the associated permutation tests more efficiently. Empirical results show that the Lancaster test statistic is a suitable substitute for DHSIC to test for joint and marginal independence, while the Streitberg test statistic better captures all factorizations of the joint distribution. The study offers a rigorous and systematic approach for reconstructing high-order systems. However, it has some limitations, including the expensive computation of the Streitberg interaction estimator due to its combinatorial nature and the assumption of independent and identically distributed (IID) data, which may not hold true in many real-world applications. Future research directions include investigating the null distribution of delta DSP without subhypotheses, approximating the distribution with temporal dependence, and exploring the role of high-order interactions in causal discovery. The authors provide a comprehensive review of existing literature on higher-order interactions, highlighting their significance in understanding complex systems. They cite various studies demonstrating the importance of higher-order interactions in diverse communities, cortical activity, and neural populations. The mathematical framework for analyzing higher-order interactions is discussed, referencing works on simplicial complexes, random walks, and the normalized Hodge-1 Laplacian. Studies on evolutionary dynamics, social networks, and synchronization in network geometries are also mentioned. The concept of coupled oscillators on simplicial complexes is referenced, along with works on the neuron mixer and its impact on human brain dynamics. A unified framework for simplicial Kuramoto models is discussed, as well as classical works on the structure of the nervous system and mathematical structure in human affairs. The review concludes by referencing works on statistical analysis, including the chi-squared distribution, quantifying attribute interactions, and multivariate extensions of mutual information. The research focuses on statistical tests for independence and two-sample tests, introducing novel methodologies and their applications. Edward H. Ip, Yu-Chung J. Wang, and Yang Ninye's works on structural decompositions of multivariate distributions are highlighted, alongside Arthur Greton's contributions to kernel statistical tests of independence. Papers by Felix Laumann, Julius von Kugelgen, and Mauricio Barahona on kernel two-sample and independence tests for non-stationary random processes are also mentioned. The Human Connectome Project is a comprehensive initiative aimed at mapping the brain's neural connections. To achieve this, minimal preprocessing pipelines were developed to prepare data for analysis. One key aspect of this project is cortical parcellation, which involves segmenting the brain into functional regions based on intrinsic functional connectivity (MRI). This approach enables the estimation of the organization of the human cerebral cortex. Research has also focused on understanding the brain's structure and function through the lens of synergistic cores, which are thought to have played a crucial role in human brain evolution and cognition. Another approach is partial entropy decomposition, a method used to analyze complex systems. Furthermore, non-negative decomposition of multivariate information has been explored as a means of uncovering the underlying patterns and relationships in brain activity data. These studies collectively contribute to our understanding of the brain's neural connections, functional regions, and organization. The insights gained from these research efforts have the potential to shed light on the intricate workings of the human brain, ultimately informing strategies for improving brain function and addressing neurological disorders. In the appendix, Proposition 1 is proven through the introduction of Lemma 2, which states that if P1D can be factorized as pi P1I-1, I plus 1D for arbitrary I, then increment DLP equals 0. To prove this, a shorthand convention for expression partitions is adopted, where a partition, x1, x3, x2, x4, is written as 13, 2, 4. The partition 1, 23D is denoted as pi. The Mobius coefficients for the partial partition lattice are defined, with micro, sigma, 1, equal to, minus 1, d minus 1, d minus 1, if sigma equals 0, and minus 1, sigma, minus 1 otherwise. The partial partition lattice is constructed by factorizing one variable out of the joint distribution, resulting in a lattice with d levels. When P1D equals P1P2D, the partial partition lattice associated with Lancaster interaction collapses into a simpler lattice. Partitions not refining pi are transformed to sigma and pi, a partition one level down the lattice, and cancelled out with the refinements of pi due to the fact that all partitions are counted exactly once, and partitions at two consecutive levels have alternating signs. On the d-1 level of the lattice, exactly n-1 partitions are not refinements of pi, which are just enough to cancel out n-1 number of 0 at the bottom level. When P1D equals P pi s, where pi s only contains non-singleton blocks, the Lancaster interaction increment DLP equals the sum of increment BLP over all blocks B and pi s. This is not necessarily 0, unlike the Streitberg interaction. However, it will be 0 if any of the increment BLP is 0. If one singleton is factorized out of an arbitrary block B, pi s will be a partition with one singleton block, and hence increment BLP equals 0 by lemma 2. Therefore, increment DLP also equals 0. Moreover, if more singletons are factorized out, increment DLP will remain 0. The page from the research paper presents a series of proofs for key propositions related to the Lancaster interaction and Streitberg interaction in statistical analysis. It begins with the proof of proposition 2, which simplifies the mixed central moment operator expression to resemble the original Lancaster interaction. This simplification yields distinct terms with coefficients dependent on the number of occurrences of 0. Next, the paper addresses the proof of proposition 3, where the Lancaster interaction estimator is computed directly from the estimated norm of the mixed central moment operator. This computation involves summing over all possible combinations of indices and applying the phi function to each term. Following this, the proof of proposition 4 is presented, which can be achieved through manual expansion or by utilizing the relationship between Lancaster interaction and Streitberg interaction as stated in Lemma 1. This proposition essentially expresses the Lancaster interaction as a sum of Streitberg interactions across different partitions of the dataset. The paper also covers the proof of proposition 5, focusing on computing the norm of the mixed cumulant operator. This is done by squaring the mixed cumulant operator and using the product lattice discussed in section 4.2 of the paper. The resulting expression consists of a double sum over partitions pi s and pi s, with each term involving the product of phi functions applied to different indices. In summary, this page provides detailed proofs for several key propositions in the paper, including the simplification of the mixed central moment operator, computation of the Lancaster interaction estimator, relationship between Lancaster and Streitberg interactions, and the norm of the mixed cumulant operator. These proofs are crucial for understanding the statistical properties and relationships discussed throughout the research. The authors introduce the concept of a product lattice, constructed by taking the Cartesian product of two identical reduced partition lattices, each containing partitions with no singletons. This product lattice is an upper semilattice, where the order relation between elements is defined as the product order. For D equals 4, the product lattice contains 4 partitions with no singletons. P1234, COVALENT P12 P34, COVALENT P13 P24, and P14 P23. Figure 4 illustrates the product lattice for D equals 4, with dark green and dark red highlighting elements in L, and light green and light red representing elements in L. The order within each element is not informative in this case, as the kernel matrices are symmetric. The authors utilize the product lattice to directly compute the coefficients of the estimator in proposition 5. The resulting estimator using centered kernels when D equals 4 is given by a complex expression involving kernel matrices and summations over indices. Some terms in the estimator are summed up twice due to the symmetry in the product lattice. The authors also discuss the composite null hypothesis, where the permutation test strategy involves multiple subhypotheses, and the rejection of the interaction is confirmed once all subhypotheses are rejected. By considering the lattice structure, the authors show that only 2D11 subtests of factorisations corresponding to the second level of the partition lattice need to be performed, rather than considering all possible factorisations, BD, for the subhypotheses. This allows for a more detailed understanding of how the joint distribution is factorized in the case of rejecting the Streitberg interaction. In the context of factorization, the space of all possible ground truth factorizations is denoted by pi d. When performing subtests, rejecting a subhypothesis eliminates the refinements of the associated partition pi. This is illustrated by the partition lattice of 4 variables, shown in Figure 5. The lattice structure arises from the refinement ordering, indicated by dashed lines. For instance, rejecting P1 P2 3 4 automatically rejects P1 P2 P3 4, P1 P3 P2 4, P1 P4 P2 3, and P1 P2 P3 P4. The remaining partitions form a lattice, which can be simplified by collapsing singletons, yielding a reduced partition lattice that reflects the simplification of operators. However, this should not be confused with the full lattice associated with the test procedures. The Mobius function, a crucial component in this framework, can be computed using the expression provided. To validate this expression, one can compute it on the trivial partition lattice associated with joint independence, providing a baseline for comparison. This approach enables the efficient computation of the Mobius function, a key step in the factorization process. By leveraging the lattice structure and the Mobius function, researchers can navigate the complex space of possible factorizations, facilitating the identification of underlying patterns and relationships. In the context of simplicial complexes, an aximplex is defined as a set of k plus 1 vertices, where a 1 simplex represents a line, a 2 simplex is a triangle, and a 3-simplex is a tetrahedron. A simplicial complex theta is a collection of simplices that satisfy two conditions. If theta element of theta, then all subsimplices V subset of theta built from subsets of theta are also contained in theta. And the nonempty intersection of two simplices theta 1, theta 2 element of theta is a subsimplex of both theta 1 and theta 2. This natural inclusion ordering in the subset lattice is established for simplicial complexes. The zeta matrix, as shown in Figure 6, and the Mobius matrix, depicted in Figure 7, illustrate how the boundary operators of D1 simplex can be found as block matrices within them. The subset lattice does not include non-simplicial terms, which have been numerically demonstrated to be essentially present in synthetic experiments when P1234 equals P12P34. The zeta matrix for the partition lattice of 4 variables is composed of small blocks corresponding to the boundary operators in a 3-simplex. 2 red blocks represent the edge-to-face operator and face-to-tetrahedron operator, while the blue block corresponds to non-simplicials, which are partitions with no singletons. The Mobius matrix, on the other hand, preserves the block structure seen in the zeta matrix. Each block can be obtained using the Mobius inversion on the incidence matrix of its own partially ordered set, such as 12, 34, 13, 24, 14, 23, 12, 3, 4, 13, 2, 4, 14, 2, 3, 23, 1, 4, 24, 1, 3, 34, 1, 2, which forms a partially ordered set. The values are always 1, as the partially ordered set only contains elements from 2 neighboring levels. The interplay between test power and sample size is explored through 4 experiments, each with 3 interaction strengths, to demonstrate how a decrease in sample size affects the null rejection rate. The results, illustrated in Figure 8, show that the Lancaster and Streitberg tests can accurately detect higher-order interactions with as few as 50,100 samples, depending on the interaction proportion or strength, whereas DHSIC requires substantially more samples. This provides experimental evidence that the proposed Streitberg interaction test has superior sensitivity in detecting higher-order interactions compared to DHSIC. The computational complexity of the Streitberg interaction estimator is analyzed, revealing an original time complexity of B squared dn squared d, where B is the Bell number, representing the number of partitions in a set of cardinality D. However, the lattice formulation allows for a reduction in the number of terms in the mixed cumulant operator from B to F, resulting in a complexity of F squared dn squared d. This reduction is illustrated in Table 1, which presents the number of terms before and after eliminating partitions with singletons. Furthermore, for fixed D, the time complexity can be optimized by optimal contraction ordering, taking advantage of the fact that 2 index sets are disjoint. This reduction for different D values is presented in Table 2, where n squared D becomes nmin pi s plus 1. This optimization enables efficient computation of the Streitberg interaction estimator, making it a viable option for detecting higher-order interactions in complex systems. The time complexity for Dorder interaction estimators, specifically the Lancaster and Streitberg methods, is a crucial aspect in understanding computational efficiency. The Lancaster method, when centered, can be computed in dn2. Demonstrating its efficiency in detecting high-order interactions that significantly impact network structure and dynamics. In contrast, the Streitberg method, after optimization, shows a time complexity of n2 for D-way interactions. This optimization highlights the practical importance of detecting high-order interactions, which are essential in various fields such as neuroimaging. In neuroimaging data analysis, preprocessing is critical and involves bias field correction, functional realignment, and motion correction. This is evident in the Human Connectome Project data, where accurate detection of high-order interactions can reveal intricate patterns within the brain's neural networks. Moreover, reducing computational cost by discounting certain high-order interactions when lower-order interactions are present is a practical consideration. This approach not only simplifies the analysis but also enhances the reliability of the results. Overall, The refined time complexity of these estimators underscores their utility in understanding complex systems, emphasizing the need for efficient computational methods to unravel the intricacies of high-order interactions. In the realm of fMRI data preprocessing, a pivotal step is the removal of noise and spatial normalization to the Montreal Neurological Institute (MNI 152) standard space. This process is followed by denoising using the anatomical comp-core method, after which the data is parcellated according to the Schaefer 100 atlas. The resulting volume is then spatially averaged across all voxels in the same region for each time step. Table 3 illustrates the computational time required for all fMRI experiments, revealing that the time taken increases with the number of ways in the interaction. All experiments were conducted on a 2015 iMac with a 4 GHz quad-core Intel Core i7 processor and 32 GB 1867 MHz DDR3 memory. The analysis of simple hypergraphs is also presented, where individual regions are nodes and high-order interactions define hyperedges. This approach integrates information across orders of interaction and can be analyzed by computing structural properties of hypergraphs. Degree assortativity of the different hypergraphs is shown in Figure 9, revealing that almost all RSNs display a negative degree assortativity, with the exception of the FPN showing positive degree assortativity for higher-order hypergraphs. Future studies will explore the links between high-order interactions in brain activity and different functional areas. An alternative hypergraph construction is proposed to interpret the presence of lower-order interactions in larger clicks. This involves identifying purely synergistic, or emergent, interactions, purely redundant interactions, and interactions with both synergy and redundancy. This construction could offer an alternative perspective on the data, providing insights into the relationships between variables. The research focuses on a statistically motivated approach to computing synergy and redundancy, a crucial area in computational neuroscience, utilizing hypergraphs for representation. This involves a statistically motivated approach to computing synergy and redundancy, which is a significant area of research in computational neuroscience. The methodology includes code for interaction tests and synthetic experiments, available in an anonymous GitHub repository.